Hi, my name is Alex Piacentini. I'm from the Christopher Mendias lab at the Hospital for Special Surgery. And today I'll be talking about the MRL MpJ mouse strain and how it is not protected from muscle atrophy and weakness after rotator cuff tear. Murphy-Roth's large mouse strain has shown enhanced tissue regeneration and protection against pathological changes in disease and injury conditions compared to standard mouse strains such as Black 6 mouse. We wanted to test this strain's superhealing capability in skeletal muscle tissue and analyze the biological changes in their healing process compared to standard mouse strains. We chose the rotator cuff, as human patients with rotator cuff tears often experience substantial weakness and significant biological changes such as fibrosis and fat accumulation, which can limit a surgical repair and post-op healing. So in order to do this, we performed a full thickness supraspinatus and infraspinatus tenectomy and denervation in adult male MRL and Black 6 mice. We tested muscle fiber contractility, histology, as well as RNA sequencing and mass spec-based metabolomics and lipidomics to explore biological differences between the strains. We hypothesized MRL mice would display less muscle fiber atrophy and fat accumulation and experience less of a loss of strength after rotator cuff tear compared to Black 6 mice. So our methodology was we used 3-month-old males for MRL and Black 6 mice. As I mentioned before, we did a bilateral full thickness supraspinatus and infraspinatus tenectomy and denervation on both Black 6 and MRL strains. Muscles were allowed to heal for 30 days, and then they were harvested. So we used a 4-prong approach: histology, biologics, muscle contractility, and RNA sequencing. For histology, we used antibodies for different fiber types such as 2B, 2X, 2A, and any hybrid fibers such as 2B-2X. And we did this to determine fiber cross-sectional area and the number of fibers per type within Black 6 controls, Black 6 tears, MRL controls, and MRL tears. Now for biologics, we performed RNA sequencing. So we isolated RNA from infraspinatus muscles and used an Illumina HiSeq 2500 platform. And the RNA-seq was validated with qPCR. For metabolomics, we used a mass spec-based metabolomics, and that was performed by the University of Michigan Metabolomics Core, and Mass Hunter quantitative analysis software was used to quantify those metabolites. For lipidomics, Multiquant and MetaboAnalyst were used for quantification and analysis. For fiber contractility, bundles of muscle were dissected from the left supraspinatus during harvesting and placed in a chemical skinning solution for 30 minutes, and then in a storage solution to be stored at -80 Celsius. On the day of testing, bundles were thawed in an ice slurry, and individual fibers were pulled from bundles using very fine forceps. And this was done in a relaxing solution. And the fibers would be attached to a servo motor provided by Aurora Scientific on one side, and a force transducer also from Aurora on the other, and maximum isometric force was measured. A video sarcomere system from Aurora Scientific was used to adjust the fiber length to put the fibers at the optimal sarcomere length of 2.5 micrometers. Fiber cross-sectional area was calculated by measuring 5 different points on the fiber with images taken from top and side views. And specific force was calculated by dividing maximum isometric force by the calculated TSA. So our results for contractility and histology, the body weight of supraspinatus muscles normalized to the body weight of mice was reduced from 50% in Black 6 mice surgery compared to controls and 42% in MRL mice. So for contractility, we saw no change in fiber cross-sectional area, no significant change across fiber cross-sectional area, although specific force was 52% higher in control MRL versus control Black 6. But both groups were reduced 40% from their respective controls after the tear. So no significant change in fiber cross-sectional area. Fiber typing results for MRL mice, type 2B fibers were reduced from 50% to 36%, and type 2A fibers increased from 8% to 17%. In Black 6 mice, we have a similar reduction from 58% to 45% of type 2B fibers, and type 2X fibers increased from 27 to 35%. So our biologic results for RNA sequencing, multiple muscle fiber contractility and cytoskeletal organization genes were downregulated in both strains after tear. And many genes were differentially expressed between the strains, but were found to be either pseudogenes or are not yet annotated. As for metabolomics, glycolytic metabolites were increased in Black 6 mice after the tear, but there was only a moderate increase for MRL mice. And MRL mice also had a substantial increase in several free amino acids after tear. For lipidomics, there was a fair amount of overlap between the tear groups, although control groups were moderately diverged. And Black 6 groups showed an increase in cholesterol esters, glucosiluramides, and triglycerides, while MRL groups showed an increase in fatty acids and phosphatidylcholine. In conclusion, we found that there were many genetic differences between the two strains, but these differences brought no statistically significant or substantial improvement in muscle fiber force production or atrophy, and we found no favorable change in the lipidome or metabolome between Black 6 and MRL mice. MRL mice were thus determined to be not protected from fatty degeneration after rotator cuff tear. To dive a little bit deeper into this, MRL mice, as I mentioned before, had higher specific force values compared to Black 6 controls, but both strains experienced a 40% specific force decrease after injury. This reduced force production is consistent with the general reduction in contractile and muscle fiber cytoskeletal genes and muscle regenerative genes that was shown in RNA sequencing. And we also found no difference in markers of fibrosis between MRL and Black 6 mice after tear. Metabolomics and lipidomics have not received a lot of attention in the context of rotator cuff tears, despite lipid accumulation being consistently associated with rotator cuff tears in other studies. Our findings indicate that Black 6 mice may shift toward glycolytic metabolism after rotator cuff tear, while MRL mice may shift to greater amino acid and ketone metabolism after tear. So we've clearly demonstrated these species and strain-specific changes in both the metabolome and the lipidome after rotator cuff tear. So despite these numerous genetic, metabolomic, and lipidomic changes between these two strains after injury, we found no functional difference between MRL and Black 6 mice after rotator cuff tear. Our results indicate that fat, which accumulates after a rotator cuff tear, likely occurs due to deficits in lipid oxidation. Other findings have demonstrated intratendon healing in MRL mice, and this may lead to improved tendon-to-bone insertion site healing. And future directions might be finding these biological pathways that lead to that improved function in intratendon healing, which can lead to new therapies for rotator cuff, although, as our study demonstrates, those therapies will most likely not be affecting muscle regeneration. So I'd like to acknowledge some other members of the Medias lab here at HSS, as well as the Rodeo lab, specifically Dr. Rodeo and Dr. Susumu Wada for their help with surgeries, Dr. Josh Dines, Aurora Scientific, and Matthew Borkowski. If you'd like to hear more about this research, you can contact me via email or Dr. Mendias. And thank you so much for listening.